Now we'll be looking at just for a reference purpose and to understanding the proofs that we have available for us with this equipment here. We'll just briefly look at them. So to understand the different types of probe design and their application and all that, that is a separate course entirely. So this is just an overview of the probes we have here. So this one is a conductivity probe. For this probe, the cable and the probe are all fused together as one unit. So this is for conducting a conductivity test for various material, maybe for material sorting or for to determine its treatment or to determine the grade of a different material using their conductivity. That is what you use this probe for. So it's not for flaw detection, which is a determination of cracks and any in service defect. This also is not a surface probe, so do not use it as a surface probe. You can see the coil at the center for conductivity check, so not a surface probe. It is clearly written here, conductivity. Do not use it for surface inspection. The next probe we have here is our normal surface probe now. So this is our surface probe, and I can take this out. You see the probe design. Okay, I'm gonna take it out. But if you open it, this is our normal surface probe. You see Olympus and the serial number and the frequency range. So this is the frequency range from 300 Hz to 10 kilohertz. If one major thing you find major difference you find between surface probe and word probe, it's the frequency. The surface probe usually have very low frequency compared to the word probe, because you are scanning, let's say this is the surface you are scanning, you are just looking for very tiny crack. You need low frequency with less noise to be able to find crack on the surface, especially when you are using for aircraft application to look for tiny cracks in maybe aircraft wings, or you are doing checks on the wheels, or maybe very sensitive engine parts. You want to be able to find those fine cracks before they start developing. So this is the surface probe. If you can see, this paper comes with it. This is a technical data sheet. If you look at what is written here, for people that don't want to stress themselves, you can just pull out the data sheet. Look at this information that you find here and input this information straight into the equipment. It will give you the curve that you want. I normally discourage people from doing this, but if you are looking for shortcuts, just come here and fill this information. It will give you your impedance curve very quickly. That way, you can go ahead and continue your calibration process without stress. It also gives you additional technical information concerning the probe that you might find useful. So keep this back, protect it, because it might be useful for certain inspectors that will require additional information. The next probe we'll be looking at is the word probe. They come in different designs. For this one, this is the angled type, where you can also see the depression, by the curvature rather, where you can place your hand down for your scan. And it also has a bridge design where you have a coil here and you have another coil here. So this needs to be protected. This top tip is one off. So, and you can see here you have the serial number. Like I said, the frequency of the word program usually higher than that of the surface program. It's 100 to 600 kilohertz with the serial number with the PN number. So this is the word probe. This is the also the word probe, similar to the angled type one. is of the bridge configuration. So compared to the other one that is angled, this one is straight. So you can look at it. Both of them are performing the same function, but for ease of use, this one is for straight application. Why this? If you have a, let's say, looking at this wall now, it's easier for me to use it if this wall is my weld. It's easier for me to use this configuration to scan a weld that is around this area. So the frequency for this is also within the range of about 100 to 600, similar to this ones, 100 to 600 kilohertz. So that's the word probe, the bridge word probe. The next one we'll be looking at is the bolt hole. Though this unit does not have the capability to perform bolt hole inspection, but this is a bolt hole probe. This is the manual type, so it does not require you to connect to any rotary unit to use, so you manually rotate it. Per the design, you will see this is detachable. This is the probe itself, which is more like a pencil probe. And but this time, instead of having the coil on the surface, the coil is at the edges here so that it can make contact with the hole. This is a kind of a fixture so that you can, if you want to bring it up or bring it down. So the distance between this edge and the tip will be the depth of the bolt that you can, the hole that you can inspect. So if I put it here, let's say I have this as my bolt hole and I want to inspect this hole. You see this stays on the top and the probe can then rotate freely on the inside. If this is the manual probe, you have to manually rotate it. By the time it goes round, even if it is one or two revolution, one revolution, you'll be able to see where the crack is. You can still run further revolution to just confirm it. So this is manual bolt hole, but in most industrial application, you have the rotary units that you use in rotating it so that it's faster. So these are the probes. Then we have, as usual, our calibration standard, the block with the shim. These are just 3 shims. In a situation where your shims are not enough, you can even add your own shim. And in some cases, people can also you can use paper, you can fold paper. In case your lift off, this 3 is not enough, you can add paper and other materials that are non-conductive and they can form lift off for the purpose of your calibration.